So now we start potential energy. All of us have potential, even if it's only potential energy. Ha ha ha. So a quick little question. You should have already taken notes on this stuff by outlining your chapter. So potential energy is stored up energy that has the possibility of being used. So which of the following are forms of potential energy? Gravitational, chemical, heat, or elastic, which includes springs or rubber bands. If you said A, B, and D, you would be correct. The gravitational stores up energy because of its height above the Earth. Batteries store up energy through the chemicals that are inside them. And elastic, springs and rubber bands, if you stretch them, that's obviously energy, because you let it go, it's going to start moving. It uses that energy that's stored. And heat is just friction. Heat. We'll talk about heat some other time. So first, I am going to derive the formula for potential energy. It would be a good idea to know how to derive these formulas, this one and the kinetic energy formula from last chapter, because that's good questions to ask on a test. Hint, hint. So we know that work equals force times distance, and we know that the force of gravity, it's kind of weird how that came out, it should be a G. Force of gravity equals mass times gravity. So this is a very simple formula to derive. So in our work formula, instead of F, we write mg. We're multiplying that by the distance. So this distance here that we're talking about with potential energy, that's the height above the surface of something. Generally, we're going to be talking about the height above the surface of the Earth. So height above Earth. So instead of writing mgd, which is a beer, but you people should not know that, we write mgh. So this is our formula for potential energy right here. Potential energy equals mass times gravity times height. All right, and so a simple little problem. A roller coaster cart slowly crests the top of a 72-meter track. It then travels down the track until it reaches ground level. How fast is it going when it reaches the ground level? So to do this, we use our work energy theorem, which is work equals the change in energy, which equals the final energy minus the initial energy. We rearrange this so that work and the initial energy are on the same side. That equals the final energy. Energy final. So in this problem, though, work is 0. So we just have the initial energy equals the final energy. And to start off with, the initial energy, it's all potential. It's the potential energy. And the energy at the bottom is going to be all kinetic energy. So potential energy initial equals the kinetic energy final. Because energy, total energy, equals potential energy plus kinetic energy. So on this side, we do have a KEI, but it's 0, so I didn't include it. And on this side, we have a PEF, and I didn't include that because the height is 0, because it's at the ground level. The initial potential energy equals the final kinetic energy. All right, so now we plug in our equations. We know potential energy is mass times gravity times height. We know the kinetic energy is 1/2 mv squared. Look, we got an m on both sides. We can get rid of that guy. So GH equals 1/2 v squared. We rearrange this to solve for v. You get v equals the square root of 2GH. Now we plug in our numbers. 2 times 9.8 times our height, which was 72 meters. Whip out your handy-dandy calculators, and you get a velocity of 37.6 meters per second. Very simple problems. Nah, not a lot of tricky stuff we can do with these guys, unfortunately for me. Fortunately for you, though. So here's actually a little GIF of that guy. If you look at the speed, it's going to hit 37.6 at the bottom. Now notice as the height changes, the height goes up, the speed decreases. As the height goes down, the speed increases. So this is how roller coasters work, using all potential and kinetic energy. So every time it goes up a little hill, potential energy increases, kinetic energy decreases. Every time it goes down, potential energy decreases, and the kinetic energy increases, because kinetic energy deals with speed, and potential energy deals with height. So as shown in the previous example, a loss in potential energy often leads to a gain in kinetic energy, leaving the total energy constant. You might guess that energy is conserved, because it is. We call this the conservation of energy. We don't lose any energy, so the initial energy equals the final energy. So here's another little problem. Here's a little guy in a loincloth known as Tarzan. He falls out of a tree from 5 meters up, grabbing a vine on his way down and swinging. What is his velocity at the bottom of his swing? Man, I got all kinds of typos in here. Swing. So the first question we need to ask ourselves, can we use the conservation of energy? Another question, is there work done on the system from the outside? So, at the bottom of his swing, there is no work done on the system from the outside because the force of the vine is always perpendicular to the distance being traveled. So the force from the vine, the tension force, acts perpendicular to each point on his swing. And the cosine of 90 degrees equals 0, so therefore there's no work. So now we're actually do the problem. So just like before, the initial energy plus the work equals the final energy. But again, we just said the work was 0, so that guy's gone. So therefore, the initial energy just equals the final energy. So initial energy, kinetic energy initial plus potential energy initial equals kinetic energy final plus the potential energy final. Now he starts top of the tree. He's not moving, so that guy's 0 because velocity is 0. The bottom of his swing, his height is 0, so that guy's 0. So we're just left with the initial potential energy equals the final kinetic energy again. And just like last problem, mgh, his initial height, equals 1/2 mass times his final velocity squared. M's are gone again. You get the same exact equation. The final velocity equals the square root of 2gh. Plug in some numbers. You get 2 times 9.8 your gravity times your height of 5 meters. So you get a velocity of 9.89 meters per second. Pretty simple. So let's say he just fell out of the tree and didn't swing. What would his velocity be if you were in free fall for that distance? So we can go back to our kinematics equations and make a little chart for the y direction. So his initial velocity in the y direction is 0. His final velocity is what we're trying to find. Is delta y, goes down -5 meters. And gravity is just gravity, which is 9.8 meters per second squared. So then we use this equation, the final velocity squared equals the initial velocity squared minus 2g delta y. This guy is 0, so we're just left with the final velocity equals the square root of -2g delta y. So the final velocity, same thing, -2 times 9.8 times -5. So it's exactly the same as we had if he was swinging. So he has a final velocity of 9.89 meters per second. So you can see that most of these free fall problems that we've done before, you can now use kinetic and potential energy for. It's actually a lot easier to use kinetic and potential energy, which is why we do the free fall stuff first, because we like to get the hard stuff out of the way. Alright, so here's a little conceptual problem. It's a lot trickier than the last couple we just did. So a student throws the ball upward where the initial potential energy is 0. At a height of 15 meters, the ball has a potential energy of 60 joules and is moving upwards with a kinetic energy of 40 joules. Ignoring air resistance, the maximum height achieved by the ball is most nearly what? So to do this problem, it gives you a lot of information, and it doesn't give you a lot of information at the same time. All it gives you is a height of 15 meters. You have 60 joules of PE and 40 joules of KE. But we don't know the mass, we don't know what the velocity is, we don't know all kinds of crazy stuff. So this one's a little tricky to figure out. So the solution for this guy, you have to realize that the total energy is that 60 joules plus the 40 joules. Is potential plus is kinetic. And 100 joules is what you get there. So if you realize this, and you use the conservation of energy, you know that the additions of his energies at every point is going to be 100 joules. Alright, so if this adds up to 100, then 60% of it, 60% PE, and 40% KE. So if we know at 15 meters, it has 60% of its max potential energy, and therefore 60% of its max height. Max height. This problem is simple if you just realize this kind of stuff. So 60%, use a decimal as 0.6, so 0.6 of its maximum height equals that 15 meters. And it's just the maximum height equals 15 meters divided by 0.6. So you get a max height of 25 meters. A lot of work for, a very simple problem that if we just gave you the mass, it'd be very easy to figure out. So we're going to talk more about energy conservation. So here's a little skier. He goes down a hill, he makes a jump, and he flies through the air, and then he lands. So how much kinetic energy and potential energy does the skier have at each point? So this one's easy to figure out. Part A is not moving, so it's all potential energy. So if we figure out the potential energy here, it'll be easy to figure out potential energy everywhere else, and the kinetic energy. Because this potential energy at point A is going to be the total energy the entire time, because energy is conserved. So MGH, 51 times 9.8, I'm just going to use 10, it's a little easier, times 10 times 100, you get a maximum of 51,000 joules. So that's at this point right here. So we know at each point, when we add his potential and kinetic energy up, it's got to equal 51,000 joules. Now it's a pretty simple problem. I guess I used 9.8 whenever I did this. So 50,000 joules, we'll call it 50,000. Use 9.8, that's what it roughly gets. So we start plugging in some numbers. You find out that at point B, his kinetic energy is 20,000 joules. Potential energy is 30,000. Those add up to 50. We're good. So all of these, they add up to 50. And I'll show you how we get these numbers. So at point A, we're trying to figure out how fast he's going. So we know at point A, he's going 0 because he's not moving. He has 0 kinetic energy. At point B, his kinetic energy equals 20,000 joules. So we plug that in, 1/2 times mass times velocity squared, solve for velocity, we get 28 meters per second. Similarly with part C, we get 37 meters per second. D, again, we get 28 meters per second because it's the same height as B. And at point E, all of his potential energy has been converted into kinetic, so therefore we have 50,000 joules equals 1/2 mass times velocity squared, and you get 44.3 meters per second. So I'm just going to do find the potential energy for part D real quick. We know it's mass times gravity times height. So 51 times 9.8 times 60. So you get potential energy of 30,000 joules. So therefore 50,000 minus 30,000 gives you 20,000 joules for part D. So that's how we get all these other numbers. Usually we're going to find the potential energy first, subtract that from the total energy to get the kinetic energy. And then we come down here, whatever that energy is equals 1/2 mass times velocity squared, and we just solve for V. So here's one on a ramp. We love ramps because we love stuffs at angles. But do these angles even matter in this problem? I bet you they don't. So a 2 kilogram block released from rest from the top of an inclined plane. There's no friction between the block and the plane. How much work is done by the gravitational force? So we know that work equals the change in energy, which equals potential energy. Because up here at the top, it says it's released from rest. So therefore, it has no kinetic energy. So it's just going to be equal to potential energy. MGH. 2 times 10 times 3. You get a total work done to move it to the bottom of 60 joules. What is the speed of the block? So we know all that potential energy is converted into kinetic. So at the bottom we got 60 joules equals 1/2 times its mass, which is 2, times V squared. Solve this guy for V, you get V equals, this guy's just 1. 1/2 times 2 is 1, so we just get 60 joules equals V squared. So square root of 60, you get a velocity of 7.7 meters per second. That's about as hard as the problems get. Oh, I left room for myself to do the work there. Oh well. Alright, so if I take a stapler and I slide it across the table, it comes to a stop fairly quickly. This is due to friction. Energy loss due to friction is easier to calculate because the force of friction is not difficult to measure. We need to remember our formula from the force of friction. It's pretty simple. So we're going to apply that same principle to this. So a block of mass, 50 kilograms, moves on a rough horizontal surface. Therefore, since it's rough, there is friction. And that friction applies a 250 Newton force. The travel distance is 20 meters. How much work is done by the frictional force? So we should remember work equals force times distance, and also equals force times the cosine of the angle. This angle here is 0, so that cosine is 0 just equals 1 times the distance. So we still just end up with force times distance. So the force is 250 newtons. The distance is 20 meters. So we get work equals 5,000 joules. And it's negative work because it's friction slowing it down. So 5,000 joules. And there's the same thing. That's it.